Alright, welcome everybody, both of you, to IS-50B, the most B of all IS-50s at our campus. Last time we talked about BVH as a acceleration structure. So what's going on behind the scenes when you're doing ray tracing and a lot of other game engines is that you have sort of a hierarchical... Does my mouse work? Nope. Is this not on? Or this cable's jacked up. There we go. Yeah, it is. Oh, the cable is messed up. Oh, no. That's not good. Oh, dear. Am I going to have to use my mouse? I guess so. No, it's on again. Okay. There we go. All right. So last time we talked about BVH, which you have like a nested series of boxes, basically. And these things could be axis aligned, which means that they go along the x and the y axes, or they can be axis aligned bounding boxes, which is also known as an AABB, or they can be an oriented bounding box, which would be something like this. Oh, that's a terrible rectangle. Let's try that again. There. So that is an oriented bounding box. And so the math is actually very similar for both of these. If you have an OBB, you can convert it to be an axis-aligned bounding box by just rotating by theta. Like whatever the angle is here, you just rotate it, doing the rotation, linear algebra we learned last semester, and then you've got all the math for the AABB works the same. You have to decide whether or not the extra trigonometric cost is worth having tighter fit. Like if you have like a car or something like this, or a truck, let's do a truck there, like that. And you converted this into a BVH, you'd probably slap a box around the whole thing, and then a box around these things, and this is pretty axis oriented. So you're going to be pretty good. Now for this one, you might want to have an OBB, right? Have it kind of oriented that way, and then have like one more like this or something like that. OBBs give you a better fit to the geometry, whereas AABBs make the math simpler to process and stuff. So there's kind of a trade-off between the two. There's no one right answer. You guys understand these concepts here of an OBB and an AABB? These are very commonly used terms in game development. And the math, is very similar to them. You just have to do a little rotation first. Okay. Yeah, are these automatically set up? Well, depends. Yeah, they're tools for generating BVHs. And so BVH is just a bounded volume hierarchy where you've got like boxes inside of boxes inside of boxes. But yeah, there's tools that take geometry and generate a BVH for it. And some of them can even kind of run in real time. So as these things rotate around, you might, have a better, like a box like this will fit very tightly with a AABB. But if it like rotates through space, now all of a sudden your bounding volume, gets less efficient, and you might end up subdividing and creating. If you're doing this every frame, it can be kind of annoying. And so an OOBB is nice if you have a nice tightly fit box, and then as it rotates and moves around the world, your bounding box just moves with you. So that's another benefit to an OOBB, is that as your objects move and rotate, it can move and rotate with them. AABBs can only slide around and get bigger. Right? So yeah, good question. Are they automatically set up? The question for today is, how do we know if we're doing hit scan, right? Like we talked last time about having BVH for a world. Let's say that we've got like some sort of warehouse and there's a couple boxes in here, and we want to shoot a gun, hit scan weapon like this. And this is a BVH bounding box, and then the crates inside of the warehouse are actually real, and so these are nested sub AABB bounding boxes that tightly fit the containers. How nice. Do you guys understand the what we're wanting to do here? The player over here, he's got a gun and he's shooting the gun, And you want your game engine to be able to quickly tell, did it hit something, did it not hit something? And you can have a maximum distance on these things, or you can have them be infinite. It doesn't matter particularly. It's sometimes more efficient to do a maximum range on it so that it doesn't just keep going, checking other things. So Bryant, Corrente, you guys understand what we're wanting to do here? The user shoots a gun, and we want to return, aha, we got a hit here. Okay. And moreover, if we did get a hit, what is the normal vector? The normal vector is pointing perpendicularly out. What is the texture that we hit, the material that we hit? You know, if it's water, maybe it goes through, right? Like maybe you have your gun go through water textures. You know, that's an option, right? If it's an explosive barrel, maybe it detonates. You know, kind of depends. So the question is, you got this BVH set up and you want to do a trace line, right? That's one of the key operations you want to accelerate, right? That's what we kind of talked about last time. There's a few things that you want to know. You want to know point contents, like what's at a point, and we talked a little bit about that last time, right? Like you have this BVH, and you can either use a hash table and quickly say, okay, that is land, that is a tree, you know, or you can use a BVH and say that is a thing, that is a thing. But traceline is that second thing over here. We want to know point contents, we want to know traceline, we want to do radius search. So table will do traceline. So if you wanted to do point contents, it's quite easy. You've got some tree structure for your BVH, and maybe it's got, you know, maybe it's a binary tree, maybe it's not. I don't know what this line here is doing, but basically, you know, this might be the big box, like, you know, that might be the big box, and then that might be the first box, and then this might be, actually, let's do it in a way that makes sense. Maybe we have another BVH that kind of wraps these two, right? Right? Does that make sense? And then that one's you. That one's this intermediate thing here. That one's this one. And that one is this one. You guys understand? And then basically, when you do a trace line, the first thing you do is you just check the top of the world. Did I hit the box? Did I hit the big box? Yes. Okay. Now I'm going to check if I hit the two kids. And there's ways you only have to check one of the kids. Like you can do it like a dividing plan or whatever. But don't worry about that for now. We'll just check the left kid and the right kid. Did I hit the left kid? Yes. Okay. Where? Here. Cool. Did I hit the right kid? No. Okay. We're done. Here's the point of impact. Yeah, you guys with me on this? And so if your BVH is well designed, you're able to determine where your line hits in order log-in time. So if you have a million boxes, and that's including these sort of intermediate things here, you can find the point that your gun hit in 20 steps or less, which is fast enough for most games. Like, you're not normally firing 500 bullets a second. You know what I mean? Like, you shoot the gun, right? Like, maybe you do 7 if you're doing like a shotgun or something like that. But that's fine. Like, our CPUs these days run, billions of times a second. You can do 140 operations. It's okay. You're not gonna hurt too much. Too many trace lines, too many particle effects flying around. Yeah, your frame rate's gonna start slipping. As I think you guys, you've played games where there's a lot of stuff going on, right? And your frame rate starts going So, yeah. But I mean, if you're just like, you got like a machine gun, it's going pop, 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 pop. This is fine. Okay. So, how do we do the actual math of intersection? How do we do the intersection math? So, do you guys remember y is equal to mx plus b? It's the slope line equation. There's another way of doing it where you can have a vector like that, and multiply it times t. And then as t gets bigger, the vector extends in that direction. That's very commonly used in game development as well. Just having a unit vector that's the direction, like the direction you're facing. It's your forward vector, right? You guys remember that? Do you guys remember in Unreal Engine, you can get your forward vector, the direction you're looking? And then you just, you can define a line as the direction you're looking times some scale, right? So either way, it doesn't matter. The only thing this can't do is vertical lines, right? Because that has an infinite slope, whereas this works fine if you're pointing north. So let's just say the slope is 1, just to make life simple, and it does kind of look like a slope of 1, right? So we got the x-axis here, you got the y-axis here, and let's just make b 0, and so it's just y is equal to x. That's the line we're shooting. Just we're going to make the math as simple as possible, right? So let's see, 1, 2, 3, 4, 5. So this is at x equals 5, and it goes up to like x equals 15. And 1, 2, 3, 4, and say it's like at y equals 4 up to y equals 14. Okay, so you guys understand the box goes from x5, y4 to x15, y14. Okay, so what point does it hit the box? How do you find that point? Right there. Mathematicians, start your engines. How do you determine the point that a line hits a box? This is called point. Not point. We're determining a point. Don't write and type at the same time. So this is called line times box collision. How do you determine where a line hits a box? There's also line times circle, which comes up a lot too, because a lot of people do hierarchical bounding volumes with circles as well. Depends on the shapes that you're making. So figuring out where a line hits a circle is another important thing. We're doing boxes today. Where does the line equal the boundary? Very good. So let's say y equals x. So what you do, there's 4 possibilities for intersection, right? That you have to test. You could feasibly get away with testing 3 of them, because if you miss the first 3, you don't have to do the 4th. Do you know why? So if you're testing this line, and this line, and they all miss, you don't have to test the 4th one. Do you know why? Yeah, because there's no way of drawing a line through a box where it doesn't hit 2, right? It has to enter through one and exit through another. Now, if your lines have width, then you could feasibly hit right on the edge here, you know. So in that case, you would test for it. So we'll just say we're going to test 4. But in general, if your lines are infinitely small, then just testing 3 of them is good enough. Okay. Because it has to enter through one and exit through another, right? It doesn't matter where you draw the line, right? It's always going to enter through one and exit through another. You might be like, well, what if it hits the point? Well, you know, again, infinitely small lines. Right? So, so how do we determine where it crosses this line segment here? Let me draw it in blue or something. So let's focus on the left edge right here. So that's where we know it hits. This left edge here corresponds to x equals 5. So what we do is we plug x equals 5 into y is equal to mx plus b, and we get y equals 5 as the result. That's the point of impact. Okay. If 5 is between 4 and 14, right? If we plugged it in and we got 20, then it's a miss. If we plugged it in and got 3, it's a miss. But we plugged y is equal to mx plus b for x equals 5. The left edge is x equals 5, right? This is the area where x is 5. We plug 5 in here, and we get the y value. The y value is between the minimum and the maximum. It's a hit. Where? There. We have a hit at 5, 4. Done. Easy. Okay. I mean, I did make the math a little bit simple by having a slope of 1 and a y-intercept of 0, but I think you get the point here, right? Like, even if I had a slope of, I don't know, a slope of 2, and let's see. Let's say we have a slope of 2 and a y-intercept of 3. Looks something like this. So this is y is equal to 2x plus 3. Does this shot hit the left edge? And if so, where? We're doing 2D right now. It's the same principle in 3D. It's just easier to draw 2D. So, does this shot, the hero just did a trace line, slope of 2, y-intercept of 3. Does this line hit this box? Yes or no? Yes, at 5, 13, yes. So you plug in x equals 5, 5 times 2 is 10, 10 plus 3 is 13, 13 is between 4 and 14, that's a hit. So we got a hit at 5, 13. Good. That's it, and you just do that test. And then you do it the other way for the horizontal lines. You would do like, you set y equal to 4, and then you solve for x. And so you subtract the b out, divide by y, right? You just basically plug in, like for the vertical lines, you plug in x is equal to 5, x is equal to 15, see if it hits. And then for these, you plug in y is equal to 4 and y is equal to 14, and then see if the x value matches, right? So like for this point here, and sometimes you want to know the exit point too. So like maybe, damn it, somebody stepped on this cable and doesn't work very well. So let's say you want to know where the exit point is, right? Like let's say it didn't hit the box here. Then you need to keep going, right? Because sometimes there's another box, like you shoot like this, Sometimes there's a box on the backside, so you need to keep going sometimes, right? So so if you want to know the exit point, where is the exit point of the original line? This one, y is equal to x. What's the exit point? No, this isn't right. It should be 5, 5. Why is it 5, 4? It's 5, 5. The minimum is 4. I was probably saying 4 when I wrote it. Yeah, the minimum is 4. So this hit at 0.55, right? So where is the exit point here? Substitute in y is equal to 14. What's the value of x? When plugging in an x, no longer returns a y within the box. So a miss would look like this. Like if you have a shot up here, then you plug in x is equal to 5 and you get y is equal to 100. That's a miss. In order for it to be a hit, the y value you get has to be between 4 and 14. Make sense? So if the value, so you plug in x equals 5, do the algebra. If the y you get is between 4 and 14, it hit. That's the hit location. It's 5, 5, not 5, 4. I don't know why I said that. Yeah, y equals 5. Yeah, okay. Yeah, okay. So what is this point here? What's the coordinate of this point? What's the exit wound? Where is it coming out of the box? Let's say this box wasn't here. Where's it coming out? Substitute in y equals 14. What's the x value? $14.31? Not for this one. For the original line. Y is just this, the simple math one. Y is equal to x. The exit wound is at 14.14, right? Because we substitute y for 14, and we check to see if the x value that we solve for, which is 14, is very easy. Is that between 5 and 15? Yes, it is. So that is the place the line comes out. The line enters the box at 5, 5 and exits at 14, 14, assuming it didn't hit anything on the inside. Okay. And if you're going to do a multi-line trace, then yeah, you'd actually do that anyway. Like you'd both hit the box. So a multi-line trace would say, yeah, we got a hit here, we got a hit here, and it keeps going. It hits another box up here, exit wound here, and it just keeps going, right? So multi-line trace doesn't stop early. Like if you're firing like a rail gun or something that blows through people, then and blows through walls, then you might possibly do a multi-trace that just keeps going, right, and returns every hit up to a maximum range. So yeah, 14, 14, good. And then for this one, the exit wound, you would substitute, let's see here, 14 is equal to 2x plus 3, so that's 11 divided by 2 is x is equal to 5.5. Okay, so the exit wound here is going to be at y is 14, x is 5.5. So is that 5.5, 14? I can't really see that. Okay. So the entry point here is x is 5, y is 13. The exit wound is at x is 5.5 and 14. So it kind of clips the corner on that. So you have to check all possible sides until you find a valid exit. Yeah. Mm-hmm. You could probably be a little bit smart about it. Like if the slope is positive, then you know it's going to be, you know what I mean? Like if the slope's positive, it's going to be the upper one, probably, right? It could be this one, but it's not going to be this one. You know what I mean? So like you could probably add some intelligence to it, you know. But yeah, check this one first and that one second. I don't know. If it's a negative slope, check this one first, then that one. I don't know, seems reasonable. If it's a negative slope, it can't be the top. Right? Yeah. I don't know if it's worth the complexity. It might even slow your code down. When you add all those if statements in, it might slow down. So that's basically it. And so if you had like a BVH like this, and you want to see what you hit here, you're like, okay, there was a collision. And so that hit the top level of the tree. And then you check all of its kids. It might have 2 kids. It might have more. It depends on what kind of tree you got. And either way, the next tier down, it's going to be like, all right, I hit that box there. And then once you're inside of the box and you're down to the actual geometry, now you can either just stop there and be like, hit. And a lot of video games do that, right? If you have a person, you know, you just got one box, you know, like whatever it hits, you know. You don't need to have super accurate collision in a lot of video games. You just don't. You know, if you've got a coffee cup, you just make it a cylinder and call it a day. You know what I mean? To do a cylinder, it's a cylinder, by the way, is a combination of a box and a circle. Take a circle. It's a circle in the XY plane. It's a rectangle in the vertical plane. That's all cylinders. And so cylinder collisions, capsule collisions, box collisions, and circle collisions, the sphere collisions are all very easy to implement. It's very easy to determine if a line hits a circle, if a point's inside of the circle, that kind of stuff. So I'm running out of time. So rather than getting into that, I'm going to talk about the notion of a convex hull. And so let's say you get down to it, right? And you're in that car's wheel base, and the wheels are like these cool hexagonal things because it's like the Flintstones or something, okay? And you've got like a triangular mesh that looks like this, okay? And you want to know if it hit, you know, you got that trace line coming in, you had your box here, it hit the box, you know, and you want to know, did it hit any of the triangles? Now, you could do a line triangle collision. That's doable. You can do that by doing what's called a line-line intersection test, right? And if you have a line segment, you know how I said you have like that vector times t thing. If the vector is this way, if the t is greater than 1, like it usually goes from 0 to 1, then it's a miss. If it's below 0, it's a miss. So you can do that with each of the lines and basically see if it crosses any of the lines. It's one way of doing it. But what I really want to talk to you about is the notion of a convex hull. So a convex hull is a polygon that has no interior angles. So a convex hull is a really important concept in game development. Convex hull, maybe it's not really important, but it's important to me. If you do this kind of stuff, you will see the term, like if you dig into the Quake engine, like it, all over the place. If you don't write game engines, well, none of this stuff maybe matters as much. I don't know. But IS50B is when I kind of reveal to you what game engines are about, if you guys are cool with that. IS50A is like using a game engine. IS50B, we sort of pull the covers aside, be like, all right, this is what's kind of happening under the hood, because you might write stuff yourself, or you might need to write code that is good, you know, and efficient and stuff like that. So in Unreal Engine, when there's a checkbox that says like use accurate collisions, right? And if you check it, then it will do the more precise and slower collision on it. If not, it uses the box. You know what I mean? So it's very possible you'll be writing your own engines. Yeah, it's possible. Or you take Unreal Engine and modify it, or you know, or you go to work for a company and they have one and you got to work with it. So getting the basics down, I think, is pretty important. So a convex hull is not this. This has a interior. This has a. It's got a left turn. Let's put it that way. So if you're looking at all the points kind of going around clockwise, all of the angles have to be clockwise turns. Okay. So this is a convex hull. It's not a regular hexagon or anything like that. But it is a convex hull. Because you go this way, you make a right turn, 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 you make a right turn. It's a convex hull. There's no gaps either. Gaps are surprisingly hard to get rid of when you're working in the floating point world, because you have a point and a point, and like sometimes like rounding error results in a very narrow sliver where they don't come together, and then the void leaks through and you get graphical glitches and things like that. It's actually a really annoying issue, floating point errors in game development. So another way of thinking of a convex hull is that anywhere you stand within a convex hull, you can see all the vertices. You see that? No matter where you stand inside of the convex hull, there are no secrets. You can see literally every point inside of the convex hull, right? Whereas if you were standing here, then there could be a burglar or whatever hiding over here, and you can't see him. Okay? Are you guys familiar with this concept? Convex hull? Okay. And so you can always convert a non-convex hull into a convex hull. You do that by finding the left-hand turn and then doing something like that. There you go. You got two convex hulls now. Right? Simple. So it's not that bad. If somebody gives you a non-convex hull, you can just, every time you find a left turn, you just do a subdivision and make it not a convex hull anymore. So, okay. And so convex hulls, if you are presented one, a question is a point inside of the convex hull or not? Right? And okay, before we get to that, which is a nice algorithm, see what this does for you. If you have a convex hull, you no longer have to check this line against this line and 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 this line, right? If you have a convex hull, guess what? All you have to check is against the edges of the hull, right? You have to do a line test for here, 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 and here. You guys with me on this? Because if it doesn't cross any of these, it can't get to the inside, right? So this would be called a line intersect. And you can look up algorithms for these online. They're very well known algorithms and stuff like that for doing it. So line box, line circle, box circle, the list goes on. But convex hulls are kind of the most complicated thing. So you've got boxes, you got points, you got lines, you got boxes, you got circles, combinations of those things. Cylinder, like I said, is a box circle, right? It's a box circle. Take a box, times it by a circle, you get a cylinder. The most complicated thing you'll work with is a convex hull. And the reason for that is because if there's anything more complicated like this, you can just subdivide it and turn it into a convex hull, and then use all of your convex hull algorithms on the two subdivisions. Okay. So for more complicated shapes, yep, a convex hull works with just random geometry, right? The bounding boxes are all approximations, right? There's always error, not always. Like if you have a crate, like you can have a tightly fit bounding box to it. But usually if you have a person, there's like all this error right here where a bounding box doesn't, a bullet, ow, right? A bullet can miss underneath your neck, and if you have just a crude box approximation, it hit, and it missed. And so if you want an actual test for the actual geometry, you generate a convex hull for this thing, and then you do your trace line against it. Okay, and you could probably get away with, if it's sorted left to right, you can probably get away with some optimizations. But just as an example, you can just do a line intersect with the convex hull, right? And just see, okay, that's the point it intersects at. Comes in here, goes out here, call it a day. So then there's point contents, right? Is this point within the convex hull? And that's kind of a fun algorithm. There's a lot of different ways of doing this. The one that I think you guys would understand is if you consider a convex hull as being drawn clockwise, and a lot of examples do counterclockwise, by the way, just FYI. It doesn't matter. You just need to be consistent, right? So for some reason I prefer clockwise, even though most of the industry does counterclockwise. I don't know what to tell you. It just works with my brain better. So let's say you've got all of these line segments, right? You got all these edges. It's the edge of the convex hull. If you want to know if this point here is inside of the hole, what you do is for each vertex, let me do a different color. We'll draw each color in each vertex in red. Okay. So you've got these vertices here. And so what you do over and over again is cross product. You guys remember how cross product can be used to tell if something is to the right or to the left of something? Dot product tells you if something is forward or backwards. Cross product is used to tell if something's to the right or to the left. So what you do is you have point A, point B, and point C, and you take the line AB and you cross product it, that's this line here, with the line AC. If the answer is greater than, if we did AB first, if the answer is less than 0, it is to the right. If AC is to the left of to the left, it'll be positive. So if our point's over here, we get a negative number. We say it's outside. Call it a day. If it's to the right, though, then we have to do the next one, right? We do this one, and this cross product, and this cross product, and this cross product, and this cross product. And if all the edges agree, yes, that person's to the right of me, then it's inside. You understand? So if all the lines say that the dot is to the right of them, then it's inside. Because you've just done you've traced the circumference, all of them said it's to the right, therefore it's inside. You guys got it? It's just a bunch of, once you got your hole down, and the hole could just be a set of, points, really, drawn clockwise or whatever, then you just, they're all to the right, done. True, it's inside. So, how do you make a convex hull? Did you guys do this in 26 with me? Yeah, so dot product, cross product, those are your, the matrix multiplies, those are your fundamental, tools to work with. And then once you start getting into it, it's probably good to write code to see if you can find out when two lines intersect. See if you can find out when a line can intersect a box. I might even give it to you as a homework assignment. Your homework assignment this week is to do a roughed out multiplayer map. But we will be getting to programming assignments where you'll have to do this kind of stuff. So you might want to just practice. Can I figure out if a line hits a circle? Feel free to look at source code online. It's fine. Just make it make sense to you. Okay. So we'll talk next time about the. Did we do it in 26? The gift wrapping algorithm and things like that. I know that I was reading a lot of those algorithms last semester, so I think I might have given it as a homework assignment. Did we do that, Corrente? The gram scan and convex hull? Yeah. Okay. Yeah, so you've done that already. So basically, you go through and you add each point in turn to the convex hull, and if you ever make a left turn, so you start off here, you add this one, and then you add this one. Oh wait, that's a left-hand turn, so you delete that one and make this one part of the hole. You add this one, you add this one. Oh, that's a left-hand turn. Take that one out, add it to the hole. Add this one. Oh, it's the rightmost one. We're done. And then you do the same in reverse. There you go. Convex hull. Call it a day. And that's it for today. So Yeah, these are the fundamental tools that you use to build video games. And when you get down to it, they're actually not too bad. The algebra. I mean, there's a lot of text on the screen right now, but like you guys understand, like the algebra is not bad. You just substitute 5 for x and then see if the y value you get is between the minimum and maximum. You substitute 15 for x and see if the value you get is between the minimum and maximum y. You substitute 4 for y and see if the x value you get is between the minimum and the maximum. Yeah. So, when you get down to it, like all this stuff is actually surprisingly simple. And yeah, we'll just keep running through that for a while. Okay, that's it for today. Thank you for coming out, and I will see you, I guess, in class on Thursday. I'm gonna try and figure out doing more with you guys in class in 50A, but hopefully the refresher isn't bugging you guys too much. We'll be back in person next Tuesday. Thursday is still gonna be online. All right. Peace out.